Hello, good morning, everyone. We are Mazhar and Uneeb Zahid from Department of Electrical and Computer Engineering. And today we are sharing how static var compensators, in short SVCs, prevent voltage instability in real grids. We'll ground the theory in six field proven installations from CERN to Namibia to show both the urgency and the practicality of fast reactive power control. So moving on to the next slide, importance of voltage stability and role of SVCs. Voltage stability isn't academic. It's the line between resilient power and cascading failures. When voltage wobbles, sensitive equipment degrades, renewables trip, motors stall, and entire regions can dim to black. SVCs tame that chaos by injecting or absorbing reactive power in milliseconds, filtering harmonics, and as proven at CERN, shrinking brutal MBR swings into calm, stable voltage windows that keep critical machines alive. So, moving on to the next slide, that is static var compensators. And in this slide, we'll give you like an overview. So an SVC is a shunt connected power electronics based controller that continuously manages reactive power to hold bus voltage near its set point. As you all know, built from thyristor controlled reactors, TCRs, and thyristor switch capacitors, TSAs. It blends smooth inductive control with stepwise capacitive support. The result is fast acting compensation that strengthens power quality and system stability without moving parts or slow electromechanical delays. So moving on to the next slide, that is about static var compensator operations. Here's how it works. As you can see in the graphs as well, sensors track system voltage, the controller computes the needed vars, and thyristor firing angles modulate current throughout reactors and capacitors to deliver the exact reactive power required. So because the loop is fully electronic, response is in milliseconds, fast enough to chase down post-fault dips and motor stalling before they snowball. In practice, that speed translates into tighter voltage bands and fewer nuisance trips. So moving on to the next slide, Uneeb will explain it to you. And thank you very much. And you can take over now, Uneeb.
Thank you, Mazhar. So in this slide, we will discuss how SVC helps in voltage stability. SVC purpose is to keep bus voltage near a set value by dynamically controlling reactive power. When voltage drops, it injects capacitive reactive power to raise the voltage. When voltage rises, it absorbs inductive reactive power to lower it. Using thyristor control reactors (TCRs) and thyristors switch capacitors (TSCs), the SVC adjusts the thyristor's firing angle to precisely control the amount of reactive power injected or absorbed. This millisecond level response allows it to stabilize voltage instantly during sudden load changes or faults, preventing dip surges and instability in the system. Next slide, please. Yeah. So in our project, we will go through 6 different case studies, and from in the next slides, I will get into the details of the case studies. Next slide, please. Yeah. So our first case study is an installation in France at CERN power station. The main issue was in this substation was that there was a fluctuation of 14% in voltage in each cycle on 18 kilowatt bus. So to cater this problem, they installed an SVC. This fluctuation was uh, due to the fast changing loads which demands reactive power and harmonic distortions. So can you go to the next slide, please? So they installed an 150 MVR uh, SVC to preempt voltage deviations and to filter out harmonics. As we can see on the graphs, I'm particularly talking about the graph with the green line, we can see that the voltage is stabilized around 1 per unit. And on the right side, we can see the SVC output. We can see the firing angle of the SVC. We can see the induced or absorbed reactive power by the SVC. Due to this fluctuation was significantly dropped down from 14% to 0.75%, and it increased the system's voltage stabilization. Next slide, please. Yeah, so our second case study is an installation in New Mexico in two different substations, Roadrunner and China Draw. The main problem was in this area was that these two substation has a very weak system. Due to this weak system, it has a low threshold for fault levels, which means that fault can occur easily. And it also has a problem of voltage recovery. Like voltage was recovered slowly due to motor loads and high loads in that station. These loads demand high reactive power. To cater this problem, they installed two different SVCs in these two substations. Next slide, please. Yeah, so as we can see that they installed two SVCs, and this is the response of the one of the SVCs. And this response is when the SVCs are not interconnected with each other in those two substations. So they connected those two SVCs through a fiber link. And can you go to the next slide, please? So as we can see that this is a response of SVC when the two SVCs are interconnected with each other through a fiber link. So if you will see that the bottom red line graph, it shows that the second SVC freezes its voltage control capacity when the first SVC is calculating the fault or doing an analysis on the system voltage. So due to this interconnection of two SVCs and the installation of the SVCs, the system became strong from a weak system, and they upgraded a system to to cater the issue of high load over there. Can you go to the next slide, please? Yeah, so our third case study is an installation in Tucson electric power. Due to the high load in peak season, that is summer, the system became highly unstabilized. I'm talking about the voltage stabilization, and this instability was a threat for the collapse of the system, because the voltage was used to go below zero point 0.9 per unit, and it is not in the operating range. It was due to the high reactive demand during falls due to motor stalling and slow voltage recovery. So to cater this problem, they installed an SVC. Can you go to the next slide, please? SVC of 200 MVAR, and we can also see the system voltage is now stabilized around 1 per unit. And we can also see the SVC output, the MVR output, when it induces MVR, when it absorbs MVR. So, and it also show the TCR and TSC firing angles. Can you go to the next slide, please? Yeah, so in this simulation, we can clearly see that without SVC, the voltage was even below zero point 0.9 per unit. It is not in the operatable range. So with SVC, now the voltage is around 1 per unit, and it is in the operatable range, and it has ensured voltage stability in the system. Can you go to the next slide, please? Yeah. So our fourth case study is an installation in Paraguay in Loma Plata substation. It has the same issue, that the voltage could drop below zero point 0.9 per unit in hot months, And there was one more issue that the seasonal hydropower variation led to unstable voltage profiles. So they installed an SVC over there. Can you go to the next slide, please? Yeah, and we can they install an 150 MVAR SVC over there, and we can clearly see that the voltage is below 0.95 per unit when the demand is around 74.2 megawatts. Can you go to the next slide, please? So after the installation of SVC, we can see that even at 80 megawatt demand, the voltage is above 0.99. So it increased 132% of the load margin, and it increased the voltage stability in the system. Now I would like to my team my present member that he should explain the next two installations.
Thank you very much, Uneeb. You did a very wonderful job. And now I'll take on from installation 5, that is Barrow County SVC. It's a North Metro Atlanta's Winder primary to 30 kilovolt substation serves fast growing motor heavy loads that were failing FIDVR criteria. So with voltages like languishing below 80% for seconds after falls. So previous events had already forced UVLS and trip generators. There are like signals that the area needed dynamic war injection, not just static caps. The challenge was to recover quickly without overcompensating or exciting resonance. As you can see in the graphs as well, we have shown the actual picture of the SVC and the substation in study, and also the map where in Atlanta, Georgia, the SVC was installed. So moving on to the next slide, results and analysis. The utility installed a 0 to plus 260 MVR TSC based SVC in June 2008 using two fast-switched capacitor branches under automatic undervoltage logic with manual SCADA HMI override. So stepwise capacitive injection focuses on what matters in FIDVR and also rapid voltage lift. So without complicating the system during normal conditions, the design also tolerates a TSC branch out of service, preserving reliability and stability. So moving on to the next slide, that is results and analysis continued. So in this slide, it measured events showed recovery time improving from 4.2 seconds to 2 seconds at the slowest bus, meeting FIDVR compliance while keeping peak voltages in check. So during real disturbances, the SVC fired exactly when thresholds were crossed, stabilizing the corridor under both peak and off-peak loading. That like predictable behavior reduced the need for UVLS and cut the risk of motor stalling spirals. As you can see from the attached uh, picture as well, that's illustration of fault-induced delayed voltage recovery FIDVR criteria. You have voltage recovery, you have voltage recovery at slowest recovery transmission voltage. So it shows all the analysis of the performance, and you can see the results as well, how SVC improved the system. So now moving on to the next installation, that is going to be our last installation as well, installation 6, that is NAM Power and Eskom Interia. Namibia's 400 kilovolt link to South Africa spans 890 kilometers, loading the grid with the line changing capacitance and low fault levels that nudged resonance towards 50 hertz. As we all know, frequency is very important. The results were like dangerous over voltages. Peaks were above 1.7 per unit, and it sustained levels above 1.5 per unit during switching and recovering. So keeping the intertie reliable required fast damping, black start readiness, and near constant availability. As you can see in the picture as well about the substation and the SVC installed in the real world. So moving on to the next slide, that is going to be on results and analysis. And we have attached a picture as well that shows the voltages at different levels with SVC and without SVC, and you can see a clear cut difference in the graphs, and which tells you how stable they are and what are the results before and after. And also, I'm going to explain as well. So, an ABB SVC at AUS rated to 50 MVAR, inductive to 80 MVAR capacitive, uses three TCSRs plus standby double tune filters and a resonance controller to target near 50 Hertz dynamics built for 99.7% availability, which is a very good number. It tames over voltages during energization and falls, cutting worst case peaks from previous 1.62 per unit to 1.32 per unit. That stability enabled secure interconnection with ESCOM and safer regional power sharing across very long lines, as I mentioned, 890 kilometers. So moving on to the next slide, that would be about conclusion and analytical insights. So according to our whole study across wildly different grades, SVCs did the same essential job, delivered precisely timed VARs that keep voltage where the system can breathe. They mitigated FIDVR, expanded load margins, filtered harmonics, and neutralized resonance, what they are supposed to do, using the same toolkit tuned to local realities. If you remember one thing, let it be this: fast, intelligent, reactive power is not optional in modern networks, it's the backbone of stability. And thank you for your attention and curiosity. We are grateful to Professor and obviously Dr. Rajiv Varma for guidance. And we are happy to take your questions, technical or strategic. You can email us as well, or anything in between. Uh, let's talk about where fast war control could make the biggest difference in your grid. Thank you very much.
Thank you very much.